Okay, so two people here. On the left is Thompson, and he got really mad if you called him Thompson. If you put a P in there, right? All Thompsons get really, really very agitated. I have no idea. I'm just joking. But I know there's a banjo player called Thompson, and he even put on his website, note, Thompson is a common misspelling of my name. Okay, so banjo players get mad. The guy that discovered the electron would get really, really mad, I would think. Do you think? Okay. Anyway, there's J.J. Thompson, and he discovered the electron. Either that or maybe it is Thompson, and I just left the P up. You know, I think I double-checked, all right. This is Ernest Rutherford. Okay, two different people. But Thompson discovers the electron. Rutherford discovered the nucleus. Here's the story. Here's the story, right? Okay. This apparatus here is basically a mass spectrometer. What you can do with mass spectrometers is you can look at the charge to mass ratio of particles flying through a vacuum, right? And he discovers that these electrons have this, all of these, this is how you discover a particle, right? It's got a unique charge to mass ratio, right? And they are all small. He knew they were small. He knew they were negatively charged. And he knew that they were in the atom. So he came up with a model of the atom. Here's his model. Yes? Okay. Notice that the atom has electrons in it. Do you see that? Yeah. Do you see the electrons in the atom? Yeah. Yeah, that atom has electrons in it. Yeah. Who discovered the electron? Thomson. Yeah, and what's in his atom? Electrons. And they're small. They are very small. He knew they were small, that they were very light particles. And he knew that they were negatively charged and that they were in the atom. And that atoms were much bigger than electrons, right? 10 to the minus 10th meters, which is, you know, that's kind of big, right? Okay. And then surrounding it was this positively charged material, kind of like cytoplasm. Yes? I got that word from last period. I said, what's that goo in the cells? And they said it was cytoplasm, right? Okay. So there's this cellular model of an atom, and there's this positively charged sort of goo. And notice that the electrons are in there. Do you see the electrons? Do you see the electrons? Are you noticing the electrons? There are electrons in this atom. He discovered the electrons. That's his atom, electrons, prominently featured. Are you noticing that? Yeah. Just want to make sure you notice that, right? This is affectionately called the plum pudding model. These are the plums, that's the pudding. Yeah?
That's just a terrible one.
I know. Terrible?
Well, I mean, like, whoever came up with that.
I know, there we have it, right? Okay, so, Rutherford, that's enough Thompson. That's enough Thompson. Let's go to Ernie, okay? Ernie takes alpha particles. Now, an alpha particle is, let me introduce it to you, is a 2 protons, 2 neutrons. It is essentially a helium nucleus, but it is not gotten by ionizing helium. Okay? I'll tell you where it comes from. It's far more bizarre than that, right? But it's essentially a helium nucleus. Okay, it's got a mass of 6.644 times 10 to the minus 27th kilograms. So compared to like protons, which we now know, you know, are about a quarter of that, right? It's 2 protons, 2 neutrons. Here's a picture of one. I don't know what they look like, but there it is. There's a diagram of one. How's that, right? 2 positively charged particles, 2 neutrally charged particles, roughly the same size, right? Now, where do they come from? The ones that Rutherford used come from radioactive decay. These ginormous elements over here, these enormous ones like uranium and plutonium, okay, are so unstable that they can, by the way, they can just split in half. If you stuff, some of them are so unstable, like uranium-235, if you stuff a neutron into them, they just split. This is called fission. These are fissile materials, right? You feed a neutron in them and they're just like, I'm too big. I'm going to split apart. Yes? Okay? So some of them can just split like that, but some of them can reduce their size by spitting out an alpha particle. They will just spit out this alpha particle, 2 protons, 2 neutrons, and they all come out with a particular energy. They have spectral lines as well, right? And so that's what he's doing. Is he's got a piece of radium. Radium is unstable through alpha decay, and these things spontaneously will spit out these alpha particles, and he's going to do an experiment. He's going to take these alpha particles, which he knows are heavy and massive, and he's going to slam them into Thomson's atom. Yes? Now, Thomson's atom is electrons, yes, isn't it? Are there electrons in Thomson's atom? As a matter of fact, there are. They are the main particle in there, in fact, and they're very small. So should these very large particles be deflected very much by these very small electrons? No, but nothing, right? They're not going to be deflected not at all. They're just going to be deflected only slightly, correct? So he's going to check it out. You know, basically this is what we do in physics: is if we think there's something there, we try to destroy it and blast it apart and see what flies off. Yeah.
Is the mass 6.699 or 6?
That's a 4. These are 4s. Yeah. I'm trying to draw 4s on the board there. Okay. So here's the diagram. This is a radium source, a rock containing radium. This is supposed to be a block of lead, right? Or at least I'm led to believe that. Okay.
That's funny.
But let's, you know, and then basically what he did was he drilled a hole in there, right? A deep hole like that. And basically all the alpha particles that aren't flying straight out that hole hit the walls and aren't emitted from this, right? So this is a collimating device. Yeah, it just makes it, just mean collimated means it's all in one line, right? And he sends them in here, and this is a viewing screen. It's probably zinc sulfide is a typical thing. Zinc sulfide glows green. It's a characteristic green like of those old CRTs, right? And this is metal foil. Specifically, it's gold. You can take gold and you can roll it and hammer it so thin that I believe you can see through gold. You can make a layer so thin just by rolling it out that you can see through it. So you make it so incredibly thin. It's so malleable. And so he takes gold and he rolls it. He knows there's a lot of electrons in gold, right? At least that's the notion, right? And he rolls this thing out, and he's sure that these alpha particles, most of them are going to go straight through. So he puts the detector right here. He looks right here, and sure enough, most of them go straight through. They're not deflected at all. And he puts them off to the side, and some are deflected just slightly. And that's interesting, right? And then he puts the detector over here. Yeah. Some of them are deflected quite a lot. That's interesting. Isn't that interesting? They're not supposed to be deflected hardly at all. In fact, you know, almost never, but every now and then sometimes. Right? He puts the detector back here. Some of them are bouncing off this gold foil. Well, electrons are not going to bounce alpha particles straight back, yes?
No.
You know, and he said, what did he say? There's some great thing he said. It's like I shot a bullet at a sheet of paper and it bounced back or something like that. Well, you know, gee, alpha particles are small compared to the nucleus of the atom is quite large. For a gold atom is like, yeah, is quite large. I don't know what it is, right? Okay, but it's a large thing. Okay, sure enough, yeah, an alpha particle is positively charged. The nucleus of a gold atom is ginormous and positively charged, and it's just going to bounce it right back. Yeah, like a racquetball off a wall, right? Okay, so that's what he discovered. Here's his atom. Oh wait, sorry, one more slide, right? I got this out of my physics textbook from college. And the notion here is that most of these alpha particles are not deflected. Why is that? Well, because the nucleus is a relatively small thing compared to the rest of the atom, yes? In fact, it's 100,000 times smaller. You can't draw a picture of an atom. Can you draw something that's 100,000 times smaller than another thing? Well, if you had a printer that could put 100,000 dots per inch, which we don't, right? Do we? I guess probably if you talk about like lithography and stuff like that, right? For making chips, we can do that, right? But if you could do that, you couldn't even see the dot. 100,000th of an inch, right? So, yeah, we can't draw pictures of atoms. The nucleus is vanishingly small. They've exaggerated the size by a factor of 1,000 probably, right? At least, okay? So there it is. Notice that the alpha particles that are deflected are the ones that do what? They come close to or hit the nucleus, right? The ones that hit it dead on, does it make sense that those are the ones that are going to get closest to the nucleus? This is the closest case scenario, right? As you head straight toward the nucleus and you're like, whoa! Yeah? Yeah? That's the closest, isn't it? Whoa! There's somebody walking by. Whoa! Yeah? Yeah, okay. So that's, and these are the problems. You're supposed to be able to solve closest approach problems. But notice that these, the ones that are come off to the side are deflected a little, but not a whole lot, right? Okay. Yeah, there we go. So here's here is his atom. His atom is roughly 10 to the minus 10th, and they knew that just from basic calculations of size and geometry, right? And the nucleus, he figured out from this, was 100,000 times smaller. It was 10 to the minus 15th meters in size. And he did this just by sheer geometry and brute force and alpha particles going in and how many are scattered, right? You do a statistical analysis there, and it's not terribly hard, right? Okay, now, That's small. Is 10 to the minus 10th small?
Yeah.
That's kind of small. So how small is an atom?